Recording has started.
So today we start Unit 5. Unit 5 is ratios and basic geometry. And for today, we're just going to discuss ratios. A ratio is simply a comparison of two numbers. Excuse me. An example. I have two applied math classes. My morning applied math class has 8 students enrolled in it. My afternoon applied math class has 12 students enrolled in it. So if I want to do the ratio of morning students to afternoon students, I could write it as 8 to 12. So that's one way I could express it in the form of a fraction like that. Even though it's really not a fraction, it is a ratio. Or I could write it with a colon, 8 colon 12. Or, in this case, I could actually just use the word 8 to 12. I prefer to use the fraction form just because there are things you can do with a fraction, or that we already do with a fraction that we can do with ratios as well, like reducing them. Both 8 and 12 can be divided by 4. So we divide by 4. 8 divided by 4 is 2. 12 divided by 4 is 3. We get 2 to 3. We can do that in our other forms. We're used to doing it with a fraction, so it looks familiar. In our other forms, it can be done. It would just look a little different. Dividing both by 4, 8 divided by 4 is 2. 12 divided by 4 is 3. We get 2 to 3. And the same would happen over here. A little note on the wording over here, by the way, the 8 to 12. We would use that wording in this case because they are two separate groups. But I could have done this another way. I could have said I have 20 total students in applied math, and 8 of them are in the morning. So that would have been 8 out of 20. Or the wording over here would be 8 out of 20 again. So there's wordings here. The wording 2, 8 to 12, implies that we're comparing two things that are from separate groups. This one here, 8 out of 20, that is implying that the 8 is part of the 20. So the 20 is a large group that includes the 8, and the 8 is a group that has a special characteristic out of this 20. So there's a couple of different types of ratios that we can express. Comparing two completely separate groups, or then comparing one group that has a special characteristic out of a larger group. Normally, if we were in the classroom, I'd look at the tables in the classroom. We'll go ahead and do that anyway here. Our classroom tables are 72 inches long and 18 inches wide. So let's do a length to width ratio. Well, the length to width would put the length first. That's 72 inches. Width would be 18 inches. Now, first thing we notice, both of these are inches, so we can cancel out the inches. And both 72 and 18 actually divide by 18. 72 divided by 18 is 4. 18 divided by 18 is 1. Now, one of the differences between ratios and fractions, if this were a fraction, we would reduce it to just a 4. But it's not a fraction, it's a ratio. Even though we reduce it similar to a fraction, we have to stop here because a ratio is a comparison between two numbers. If I turn it into just a 4, there's no comparison anymore. It's not a ratio anymore. It is, however, a special kind of ratio. It's called a unit ratio. What that means is it has a number being compared to 1, to a single unit. You'll notice that there are no labels in these ratios. We had inches and inches here, but they canceled out. A ratio always has no labels or no measurement units on it, because we notice here that both of the ratios I've done, we start out with the same thing. This was students to students. This is inches to inches. A ratio must have the same labels or same units so that they cancel out, so that the ratio itself is unitless. This 4-to-1 ratio does not depend on any sort of measurement unit. It is saying no matter what unit I measure my width in, there's going to be 4 times that many in the length. So for every 1 inch of width, I have 4 inches of length, or for every 1 foot of width, I have 4 feet of length, or for every 1 centimeter of width, I have 4 centimeters of length. Whatever units I want to put in there, I can, because the ratio itself does not depend on any units. So because of that, I might have a ratio like 2 feet to 18 inches. Well, you might think, well, those units aren't the same. You're correct. This is not a ratio right now in the way it's written. But fortunately, I can convert the 2 feet into 24 inches, and it is now a ratio, 24 inches to 18 inches. Now, the inches can cancel out since they're the same unit. And both 24 and 18 can be divided by 6. 24 divided by 6 is 4, and 18 divided by 6 is 3. Now, once again, we have to resist the urge to keep reducing this like we would a fraction. If this were a fraction, this would be an improper fraction. We would change it to a mixed number of 1 1/3. For a ratio, we never do that. We would always leave it as an improper fraction, 4 to 3. Because remember, that ratio has to stay a comparison of two numbers. If we change it into a mixed number, there's now 3 numbers there. What's the comparison? So resist that urge to reduce it. A ratio will, even though it reduces similar to a fraction, it'll always stay as that comparison between just two numbers. So we have said that a ratio has to compare two numbers with the same unit. So what happens when I compare two numbers that don't have the same units? Let's say we go on a road trip, and I send you go 365 miles in 7 hours. Well, there is no way here that I can convert miles into hours or hours into miles. So I can't make it work out like I did up here. This is what is referred to as a rate, because I am comparing two things with different units. So that is the first big difference between a ratio and a rate. A ratio has to compare two numbers with the same units or same labels. A rate compares two numbers with different units or different labels. Now the second is, we had mentioned the unit ratio, but usually we just reduce things to a simplest ratio and we stop there. A rate is almost always expressed as a unit rate. The way you reduce it to a unit rate is you take the number that's in the denominator, the bottom number, the 7, and you divide by it. So 7 hours divided by 7, that's just 1 hour. 365 miles divided by 7, what is that? 52.142857.143 approximately miles. So there we have it as a unit rate. The bottom number, the second number, is a single unit, 1 hour. The reason we do that, the reason that rates are usually expressed as unit rates, is we like to abbreviate them. This is the true form of this rate. But we don't like writing it out in that fraction form. We like to do this. First of all, round it to 52.14. And instead of doing miles over 1 hour, we hide that fraction form in the units, like that, miles/hours. So it abbreviates it. In fact, we often abbreviate even further. We might call it 52.14 mph instead of putting the slash in there for miles per hour. But when we see that, let's say that on that same trip we got 24 mpg. We know that 24 mpg stands for miles per gallon. Whenever we see that, we have to think this. That is 24 miles per 1 gallon. Because over the next hours of class, when we start calculating with ratios and rates, that's the form we need it in to calculate with. It has to have that, both numbers have to be there with their labels, and we need to set it up in that fractional form like that. Well, let's look at some common rates. I just covered two very common rates with our miles per hour and miles per gallon. Another common rate that comes up that many of us will be familiar with. Let's say that in a given week you work 30 hours and your gross pay is $510. Well, that is a rate. That's $510. Our label there is the dollars with the dollar sign per 30 hours. Turn that into a unit rate. The number in the second number is the 30. Notice we're not dividing by the units. We're not dividing by the hours, just the number, just the 30. 510 divided by 30 is 17, or $510 divided by 30, I should say, is $17. 30 hours, excuse me, 30 hours divided by 30 is just 1 hour. And so that'll abbreviate, of course, $17 per hour like that. Another rate, we might have flow rates. A pump might pump at let's see here. Let's say that it'll pump 144 gallons, or cubic feet, let's do, in 12 minutes. So this is a rate of 144 cubic feet in 12 minutes. When it comes to rate, time is almost always the second number. Now I say almost always because I'm going to show you a rate in a second that's not, where the time is the first number. But generally, I would say 9 times out of 10, if not more often, if one of the numbers is a time, the time is the second number. So now to make this a unit rate, we're going to divide by the second number, the 12. 144 cubic feet divided by 12 is 12 cubic feet. 12 minutes divided by 12 is 1 minute. So that means that pump is pumping at 12 cubic feet per minute. Or CFM, that's sometimes reduced to. So we've seen a few rates here that have time involved, a couple at least. And we saw, the minutes were the second number. Dollars per hour, that was the second number. Miles per hour up above, it was the second number. And time is usually the second number. But we can't say, we've probably learned through your experiences that anytime you say that something is always that way, you'll find a counterexample where it isn't that way. That's what I want to show you now. Some companies, if you're dealing with customer service or whatever, have limits. They want it to be, they don't want you to spend more than a certain amount of time with customers. So let's say that it was in a 42-minute span, you are able to attend to, we'll just say serve 7 customers. So let's look at your customer service rate here. You have 42 minutes, 7 customers. That's real sloppy. I know, sorry about that. We're going to divide by that second number is the 7. 42 minutes divided by 7 is 6 minutes. 7 customers divided by 7 is 1 customer. Giving you a rate of 6 minutes per customer. There are companies that do make that standard of it should not take more than, so many minutes per customer for you to accomplish what you need to do. In dairy herd, I suppose you could say as you're milking, you want to average under so many minutes per cow in the stall in the parlor or whatever. There are all sorts of rates like that you could throw out there. When you're looking at feeding and nutrition, there's all sorts of ratios or rates that you would throw out there for that, for production. I'm looking at feeding. You might look at a cow that is producing 96 pounds of milk a day. By the way, that's a ratio or rate in itself, 96 pounds per day. That would be a rate. And you want to look at how much corn you're going to feed that animal. Let's say you're currently feeding that animal, trying to come up with a number that works out well, 24 pounds of corn each day. So the ratio here of corn to milk, a ratio of feed to production, we should probably say, would be 24 pounds of corn to 96 pounds of milk produced. The pounds cancel out. Both 24 and 96 can be divided by 24. 24 divided by 24 is 1. 96 divided by 24 is 4. So that's a 1 to 4. 1 pound of corn to every 4 pounds of production. Now that is drastically oversimplifying the situation. If you really wanted to get into the nuts and bolts, there's actually formulas that take into account the body weight of the animal, their production, and you can have other factors brought into it if you want. But that is a rough application. Other rates, there's a ton, excuse me, there's a ton of mechanical applications. This is where we're going to stretch your imagination a little bit because I'm going to draw a picture. Pretend that's not a horrible drawing. Now, it's not going to mesh really well, but those are gears. We're looking at a gear ratio. Now, a gear ratio actually compares the size of the gears. However, in gears, for 2 gears to mesh together, the teeth have to be exactly the same distance apart. The distance from here to here on one gear has to be exactly the same as the distance on the other gear. So to compare the sizes of the gears, all we have to do is count teeth. This gear here has 15 teeth. This gear has 9 teeth. So we have the ratio of the sizes. The way the ratios work is we do the number of teeth on the driven gear to the number of teeth on the driving gear. Well, how do we know which one's driven and which one's driving? Well, we need a little bit more information. Pretend that looks like a shaft with a little electric motor hooked to it. Right now, if we separate those gears, the 9-tooth gear is going to stop turning. That's because it is being driven by the other gear. It is the driven gear. So that's 9 teeth there. So the driving gear is the one that is more directly hooked to power. It's the one, if we separate the two gears, it will keep turning. That's the 15-tooth gear. Now, I didn't bother writing the word teeth on there because I know it's going to cancel out because they're both in teeth. But I can still reduce them by 3. 9 divided by 3 is 3. 15 divided by 3 is 5, giving us a 3 to 5 gear ratio. Now that 3 to 5 gear ratio applies to a lot of things when we describe these gears. It is the ratio of the number of teeth, the ratio of the sizes. It is also the ratio of the RPMs. It's the ratio of the torque transfer. That describes a lot of different parts of that gear ratio. Now, similarly, we could have a pulley ratio. Now, pulleys don't have teeth to count, so to calculate their size, we do have to use either the radius or the diameter. And let's say our two gears here are 4 inches and 10 inches. Once again, it is driven over driving, so assume we have a motor hooked right there. That is the the gear connected to power. If I cut the belt, this one stops turning. That makes that the driven pulley. So the 10-inch pulley is the driven pulley. The 4-inch pulley is the one that would keep turning if we cut the belt. So that is the driving pulley. The inches cancel out, they divide out, and both of those numbers divide by 2. 10 divided by 2 is 5, and 4 divided by 2 is 2. So we have a 5 to 2 pulley ratio there. Again, that describes ratio of the speeds, ratio of the sizes, again, torque transfers and stuff like that. In construction, if I look at a roof, there's actually 2 ratios. There's a pitch and there's a slope. A lot of people, even people in construction, use those words interchangeably. They are, however, different. Pitch is height over span. Well, what does that mean? Well, let's say that from here to here is 6 feet. And from here to here is 24 feet. This is the span. The distance from one end to the other. Obviously, that's the height. So the pitch here would be 6 feet over 24 feet. The feet divide out, both 6 and 24, divide by 6. 6 divided by 6 is 1, 24 divided by 6 is 4. That would be called a 1/4 pitch. Slope is defined to be rise over run. Slope is actually used in a lot of applications in math, and in almost all of them it's rise to run. The rise is still the 6 feet, because it goes up 6 feet. However, the run is from there to there. That's talking about the sloped surface. That sloped surface rises 6 feet and it runs That would be 12 feet, half of the span in this case. That's 6 feet over 12 feet. Now, slope is always expressed out of 12. That's why I chose those numbers. So the feet themselves would still cancel out, but that's a 612 slope is how that would be described. The reason they use it over 12 is because there's 12 inches in a foot. So that's saying 6 inches of rise for every foot of run, or 6 to 12. The difference is the slope is used when you make trusses, the pre-framed trusses that have all the pieces all fit together and stuff. The slope is what determines these angles that these have to be cut at, and of course for the bottom as well. The pitch is if you're doing a conventional beam and rafter system. The pitch tells us if I know the distance from one wall between walls, if I know the span, I just multiply the span by 1/4, and that's what height I need to set this ridge beam at above the top of the walls in order to get that pitch. So they are both kind of describing the same thing, just in different ways. Another mechanical application. Actually, that doesn't turn out so bad for my normal drawings. Those hopefully look like pistons. We're going to talk about a compression ratio. So let's say that this compression ratio, by the way, is the expanded volume compared to the compressed volume. The expanded volume is when the piston is at the bottom of the stroke, so that would be this example right here. Let's say that volume is 540 cubic centimeters. The compressed volume is when the piston is at the top of the stroke, that would be this picture here. And let's say that that is at, let's see here. Let's just go with 45 cubic centimeters. So our ratio here is 540, 45. Obviously, the cubic centimeters cancel out. A compression ratio is actually one of the ratios that is almost always expressed as a unit ratio. So we're going to try to just divide by the 45, the second number. It actually divides out. 540 divided by 45 is 12. 45 divided by 45 is 1. So that's a 12 to 1 compression ratio. Other ratios outside of just any application that would apply. One that you're probably all going to run into at some point is called a debt to income ratio. Now, before I actually do the example, let's talk a little bit about why a debt to income ratio is important and what it actually is. It goes into consideration when you go to borrow money to try to take out a loan. You hear a lot of fuss on television and other places about a credit score. A credit score does not determine whether you get the loan. Now, it can stop you. If you have a terrible credit score, like if you're under a 500, that means you've probably missed a bunch of payments, defaulted on a loan somewhere. Yeah, they're probably not going to give you a loan if you have a terrible credit score. But as long as you're in that, 625, 650 and above, you're probably going to get the loan. The difference is your credit score usually determines your interest rate. If you go to get a car loan and you have a 620 credit score, you'll probably still get the loan if you have the proper debt to income ratio, which we'll talk about in a minute. You'll probably get the loan, but you might be paying 7 or 8% interest on that car. The worst I had several years ago when interest rates were a little higher, I had a student that was paying 19.9%, I believe, on a car. Fortunately, it wasn't a very expensive car. Otherwise, they would never been able to have made big enough payments to keep up with the interest on it. If you have like a 725 or 750 or credit score, you might be paying as little as like 1.9% on your car loan. So it makes a huge difference. What determines really whether you get the loan or not. You could have an 800 credit score and still be turned down for a loan because of your debt to income ratio. Let's say that in a given month, your income is $3,000. And your debt, now debt does not include gas, rent is not a debt, food, all that is not debts. Debts are just that, car payment. Let's say your car payment is $400. Since some of you may end up with student loans, let's look at a student loan payment of $200. And let's do, of course, the ever-looming credit cards. Let's say we got credit cards sitting there of $300. Your total debt, if I add that all up, is $900 a month. That's your debt payments that you have to make. Now, the credit cards, obviously, you don't have to pay the whole amount every month. Most banks have a formula. They're not going to let you get away with saying you're just going to make the minimum payment. They have a formula depending on what your credit card balance is. They take a percent of that, and that's what they're going to tell you should be your monthly credit card payment. So anyway, here our debt to income ratio. We have $900 in debt, $3,000 in income. Notice that the dollars divide out. Both of those, I'm actually going to divide, this is one of the few we're actually divided by the top number to reduce it. It's kind of a reverse unit ratio. 900 divided by 900 is a 1. 3,000 divided by 900 is 3.3. This bottom number should be at least a 3. And here it is. It's 3.3. So that means you're okay here. But let's say you want to buy a house. And the house that you are proposing to buy would result in a payment of $600 per month. Actually, let's be a little more realistic. Let's do this. $300 per month. You're probably going to have a payment itself of like $500 to $600, but a good share of that payment is actually escrow, taxes, homeowners insurance. So the actual amount that what you actually pay the bank is not really your loan payment. It includes all that other stuff. As far as the debt part of it is concerned, they're only going to consider the part that's actually going towards the loan. So they take out the property taxes and the insurance and stuff like that. So let's say only $300 of that amount is loan payment. Well, your total debt, $900 plus $300 is now $1,200 a month. If we set up that ratio, $1,200 over $3,000, again, we're going to divide by the top number. 1,200 divided by 1,200 is 1. 3,000 divided by 1,200 is 2.5. This is not bigger than 3. The bottom number gets smaller than 3, they're going to say you can't afford this loan because that's going to put your debt to income ratio over where it should be. This is actually one of the big reasons why the big housing crash in 2008, 2009. Part of it was federal regulations. Part of it was other things, just careless practice. That 1-to-3 is a pretty standard ratio. The government was pushing banks to go down to a 2.5 or even in some cases a 1-to-2 ratio, which just meant that if people could make the payments, but if anything went wrong, if they had a week where they missed 3 or 4 hours of work and their paycheck was smaller by that $30 or $40, they couldn't afford their payment for the month. Okay, I have rambled on long enough. Your homework for today. In the book, page 282. This will be exercise 7.1, problems 1 through 65, the odd. Most of them are just creating ratios, reducing ratios and rates, a few word problems. Okay, so we have about 12 minutes left. If you would like to get started on that homework, I will be here to answer any questions if you want. Otherwise, if you